Hello everyone, welcome back to ptet.chemistry channel. In this tutorial video, we'll go through these AQA topical questions. In these questions on mole concept, these are about hydrated salt nickel sulfate there. So that is nickel 2 plus and SO4 2 minus. We have X number of water molecules. These are the hydrated salt. This is 2.287. We heated it up. As we think about heating up a hydrated salt, so we are going to remove the water of crystallization in the presence of heat. We're going to get anhydrous. So when we heat to remove all the water crystallization, we will get anhydrous nickel 2 sulfate, as opposed to previously we had these hydrated, sorry, not copper to sulfate, but nickel to sulfate hydrated, giving us this anhydrous nickel to sulfate. The only way we can ensure that all water crystallization has been removed when we heat to constant mass. So that means we keep on monitoring the mass of the resulting solid in the crucible that it is weighed. So basically the mass will become constant as no more water of crystallization gets given off. So the solid remaining had a mass of 1.344. So therefore the mass of water driven off has to be the difference in the masses there. So there's 2.287 gram minus 1.344 gram there. So we had 3 decimal place mass balance there. So pretty accurate, 2.287 minus 1.344. I get 0.943 gram of water. So calculate the value of the integer x. So I mean 1.344 gram must be the anhydrous nickel to sulfate. So I need the MR of nickel to sulfate from the periodic table. So that is going to be 58.7. So 58.7 relative atomic mass of nickel plus 32.1 plus 16.0 times 4. So pressing down to your calculator, I get 154.8. and also need the MR of water. So that is just 1.0 times 2 for the 2 hydrogen and 16.0 times 1. So that gave me 18.0. So to the next step, really this is about comparing mole ratio. So if I want, I can work out the mole of nickel to sulfate, which is basically the mass of it. What I have at the end of the reaction after I remove all the water crystallization divided by 154.8. And I get an answer of 8.682 times 10 to the minus 3 mole. I also have the mole of water, that is the mass over the MR of water. So that is 0.943 gram of water divided by 18.0. And this gives me 0.0524 mole. Perhaps I shouldn't run up too easily, too quickly. 5239. Last but not least, we can think about comparing mole ratio. If you see that there is X mole of water is to 1 mole of nickel to sulfate, so the mole of water is to the mole of the nickel to sulfate from the balance equation is X over 1. So on the top there is the mole of the water, 0.05239 mole. At the bottom there, you can think about these as getting to the simplest whole number ratio there. 8.682, oops, 0.05239 divided by 8.682 times 10 to the minus 3. I get 6.03 to the nearest whole number, which the water crystallization has to be to the nearest integer anyway, according to the question there. And that's it for that 4 marks overall question. In part B, there was what I mentioned there. How could the student check that all the water had been removed off when no more water of crystallization is present, when no more water of crystallization gets removed, then no further change in mass occurs. But this is a 2 marks question, so really what would the student need to do? So therefore keep heating a few times while collecting or measuring the mass of the solid mass of the remaining solid, and we heat this in a crucible, obviously. In a crucible to ensure heating to constant mass. So basically the idea is heating to constant mass such that the mass is no longer changing and therefore no more water crystallization gets given off. That's it for the 6 marks overall first question. In this second question, we have this reaction here where we have sodium azide and NaN3. We're supposed to find the mass of sodium amide. So sodium amide refers to this NaNH2. We want the 550 gram of sodium azide there. Assuming there is a 95.0% yield, give your answers to 3 significant figures. So it looks like we are dealing with reacting mass because the question does ask us to find mass. The question did give us the 550 gram of sodium azide. So really I should be thinking about mole equal to mass over MR for both of them. So the MR is for 1 unit of these. Onto the periodic table, I get 23.0 plus 14.0 plus 1.0 times 2. Pressing the calculator very quickly, 23 plus 14 plus 1 times 2, 39.0. And in terms of the MR of NaN3, so there's 23.0 plus 14.0 times 3, I get 65.0. Next up, we can try and convert this into our desired mole ratio thing, but we first find the mole of the NaN3, as that is the information given for us. So that's the mass 550 gram divided by the MR of NaN3, that's 65.0, and I get 8.4615 mole. Don't want to run up too early, obviously. The next step is the mole ratio. So we can see NaNH2 is to the mole of N3, 2 mole is to 1 mole because 2 mole of NaNH2 give you 1 mole of NaN3. This is from the balance equation. So we always compare mole ratio from the balance equation first of all. And then we have this NaN3, which is exactly at 0.4615 from the actual reaction. And we're supposed to find the mole of NaNH2. However, there is a 95% yield of sodium azide. So what we are saying is that not all the 2 mole give you 1 mole. Actually, the 1 mole there is not 1 mole. It should be 95 over 100 because this much mole of NaNH2 only give you a 95% yield there. So what we are saying is 2 mole doesn't give you 1 mole, but the 2 mole actually give you 95% of what you expect to get. So be very careful there, especially in terms of the percentage yield there. So we're going to do a cross multiply, 2 times that. So that's going to give us 2 times 8.4615 mole equal to 1 times 95 over 100 times by x. So what is x equal to? 2 times 8.4615. If you want, you can divide by the whole 95 over 100, but I am better at math, so I know that that is times by 100. As I move up the 100 to the top and the 95 goes to the bottom part of the fraction. So x equal to 2 times 8.4615 times 100 divided by 95. I get 17.81. They want the answer to 3 significant figures. So that is 1, 2, 3. So I look at the fourth one. This is lesser than 5. So there's 17.8 gram there to 3 significant figures, assuming there is a 95% yield of the NaN3 from the NaNH2. That's it for that 5 marks overall question. In a part B, so this is about a little bit about ideal gas equation. The fact that they told us is molar gas constant there. And we are talking about gas there. So the nitrogen produced, there's the gas. So we're going to talk about ideal gas equation, which is PV equal to nRT. So our volume is already given in meter cube, so that is fine. Our pressure is in kilopascal, that is not fine. You need to convert that into Pascal, which is times 10 to the 3. That is the same as multiplying by 1000. That converted to Pascal. This is degrees Celsius, so that is not fine. You gotta add with 273 to convert degrees Celsius to Kelvin there. And I'll get 308 Kelvin. I wanted the mass of sodium azide, and this is related to the mole because mole equal to mass of MR. That is for the NaN3. However, we can relate to the mole of nitrogen, which is a gas. This is the gas, and this one is from the ideal gas equation. So that is from P equal to nRT, where this is the mole of the nitrogen gas. So really, I think the first thing I need is find the mole of the gas. So that would be PV over RT equal to N. So that is just rearranging the equation there. So N equal to the pressure in Pascal, so times 10 to the 3 Pascal, multiplied by the volume, 7.50 times 10 to the minus 2 meter cube is the correct SI unit in this ideal gas equation. 8.31 joule per Kelvin per mole. That would mean that my temperature would have to be in Kelvin as well. Overall, that should give me 150 times 10 to the 3 times 7.50 times 10 to the minus 2 divided by 8.31 divided by 308 Kelvin. I get 4.3954 mole. This is of the nitrogen gas. So this belongs to the gas, and because this is the gas and I have 3 moles of gas coming from 2 moles of sodium azide, we need to do the correct mole ratio as usual. Correct mole ratio there. So NaN3 is to the N2. We could see that 2 mole of NaN3 give you 3 moles of N2 there. So I have the mole of N2, which is 4.3954. I just don't know the mole of NaN3. Let this be X. We're going to do a cross multiply. So 2 multiplied by that equal to 3 multiplied by X. So 2 times 4.3954 is equal to 3 times X. So X is equal to 2 times 4.3954 divided by 3. And I get X, which is the mole of, this is the mole of sodium azide. As I mentioned earlier, the mole of the sodium azide is equal to the mass over the MR. You want the mass of the sodium azide, so this means that the mass is equal to the mole of the NaN3 multiplied by the MR. And of course, we can work out the MR of NaN3. So straight onto the periodic table, 23.0 for the 1 sodium plus 14.0 times 3. I get 65.0. In fact, I think earlier I have obtained this as the earlier part of this question, which is 65.0. So really, it's about the second part of the question. So you should be able to relate to the first part of your question to begin with. So putting in the mole, putting in the MR, and I should get the mass of the sodium azide. Remember that what is appropriate number of significant figures. So this is way more than appropriate. They do not mention how many significant figures, but look at the data here. This was 7.50, so 1, 2, and 3 significant figures. So what other data do we have? We have 1, 2, and 3 significant figures for the molar gas constant. So I'm going to just run out my final answer to 3 significant figures. 1, 2, 3 from the front. So this gives you 190 gram to 3 significant figures for the sodium azide and NaN3. But first, relating to the ideal gas equation to find the mole of the gas. And once you get the mole of the gas, use mole ratio to work out the mole of the solid NaN3, and then use mass over MR to work out the mass of the NaN3 required for that 6 marks overall question. We have a part C to this question. Calculate the concentration of this nitrous acid used. So concentration there refer to a solution chemistry. The fact that we have solution chemistry, this is N equal to C times V. But be very careful. The C there is your concentration in mole per dm cube, which also means that our volume has to be of the solution, and this has to be in dm cube. So convert CN cube to dm cube by dividing by 1000. We have a solution chemistry as we were told. We have the mass of the sodium azide. So we have to use molecule to mass over MR for the solid. We have to use molecule to concentration times volume for the solution. So for the sodium azide, first of all, there is your mass over MR. We already gotten our MR from the previous part of the question, NaN3. The MR of NaN3 sodium azide was 65.0. This is simply a continuation of previous part of the question. So we can just work out the mole. and get a lot of decimal places. Don't round up too early, so don't need too many decimal places, but reasonable amount before you round them up. NaN3 is to the nitrous acid, which is the HNO2. So 2 is to 2, but the simplest ratio is going to be 1 is to 1. So this is the simplest mole ratio. So this would mean that, the mole of the HNO2 is equal to the mole of NaN3 because of the 1 is to 1 mole ratio. Therefore, that is equal to 2.30769 mole. And we want the concentration of the HNO3. We have the volume of it 500 cm cube. So that is 500 over 1,000. Which also means that you can divide the whole lot, so 2.30769 mole divided by 500 over 1,000. Make sure you use a bracket so that you don't make any unnecessary mistake there. And I get a final concentration as 4.61538. Too many significant figures, just rounding it out to 3 sig fig, just to be consistent with the previous part of the question. This is 5 for the fourth significant figure, so it becomes 4.62 mole per dm cube as the correct unit for concentration there. Nitrous acid decomposes on heating, balance the equation. So we can see that there is NO and NO3 there, so definitely the number of N that has to balance that. So if I start off with 1 and 1 just to see whether it will work or not, and I will have 2 nitrogen, so therefore I can put a 2 there. And I'll have 4 oxygen. 3 plus 1 plus 1 does not give you 4. So perhaps I need more than just that. I'm going to try something different. I'm going to try oxidation number, which you will have learned anyway in A Level chemistry. So hydrogen is plus 1 there. Nitrogen is unknown. 2 oxygen. Each oxygen is minus 2. The overall is 0. Nitrogen there is plus 4 minus 1 is plus 3. And then here the nitrogen in HNO3, so there's plus 1 plus nitrogen plus 3 times minus 2 equal to 0. Nitrogen there is plus 5. And in NO, you will have nitrogen plus minus 2 times 1 equal to 0. There's nitrogen plus 2. Here you can see that the changes in oxidation number must be balanced up. Plus 3 to plus 5 is plus 1. And then you will have plus 3 to plus 2. Oh, hang on. I think I did something wrong there. The pink color one should be plus 2. And then the blue color one should be minus 1. Which means in terms of lowest common multiple, this has to be multiplied by 2. Therefore, I'll have 2 lots of these and 1 lot of these, which give me 3 nitrogen. 2 nitrogen plus 1 give me 3 nitrogen. This is called using changes in oxidation number to balance, well, redox equation. In particular, this particular equation there. So 6 oxygen, 3 plus 2. Therefore, I just left with 1 more oxygen there. 2 hydrogen plus 1 more hydrogen, 3 hydrogen, 1 mark balance equation. Probably easier than using this method, to be honest. The next part of this very, very long question. Sodium azide has a high melting point. High melting point there refers to giant structure. The reason there must be giant structure. Sodium azide consisting of the metal ions, which is so sodium azide, it has a giant ionic lattice structure. So number 1 is always structure and also bonding. So state the structure first. Of course, you have strong ionic bond. This is between the oppositely charged ions, where you have Na plus and then N3 minus, Na plus, N3 minus. These are the alternating cations and anions, which you have learned from your IGCSE or O Level or whatever 14 to 16 years old chemistry that you did. So there will be your cation, there will be your anion. So giant ionic lattice structure, therefore melting it. So what are we doing? When we melt it, it requires a large amount of energy. A large amount of energy. What are we breaking? We are breaking strong ionic bond. So we are trying to justify what exactly we are breaking in order to justify the very high melting point. And this is ionic bond between the oppositely charged ions, between the cations and also anions. You can say that, or you can just straight to the point and say between the Na plus and also N3 minus oops, sorry, not that N3 minus. There are 3 nitrogen atoms and a -1 charge, and therefore it's Na plus and then N3 minus, such that you get NaN3 in the formulation earlier. This next part, we're supposed to draw a coordinate bonding. So you have an N3 minus. You could see that this nitrogen triple covalent bond, no problem. But here, this is nitrogen with 1, 2, 3, and 4 covalent bond. That is the problem. We're going to show the donation of the lone pair, and essentially we are donating towards this nitrogen, as this nitrogen form 4 covalent bond there. Now give the formula for molecule that has the same number of electrons as the azide ions. Molecule number 1, so that means uncharged, and then number 2, you're looking at same number of electrons. So first of all, we have 3 nitrogen. The whole thing is -1, so we will have 7 plus 7 plus 7, which is 21 protons, but the electron counting will be 21 plus 1 because you are gaining 1 electron, so that's 22 electrons. I wonder, 22 electrons. So if you look at 22 electrons molecule, let me think. CO2, there's 6 plus 8. That doesn't quite work. You want 22. 22. HF, HCl, that doesn't quite work. H2O. Okay, this is a bit tricky. What am I looking at? What am I missing out? Let me think. N minus. How about 7, 7, and 8? 7 plus 7 plus 8. This gives you 22 electrons. So 7 protons, 7 electrons. That is nitrogen. There's nitrogen. There is oxygen. That is our N2O, so that is acceptable there, I guess. Last but not least, very, very long question now. What is the formula of magnesium azide? We know it was Mg2 plus for group 2 metal ions, where you will lose the 2 electrons in the outer shell. And now you have N3 minus, as stated in the previous question, -1 charge, and then 3 nitrogen atoms in one of these ions. We look at the charges of these ions, which is 2 plus and -1. So we bring down the 2 and the 1. We are doing lowest common multiple as we exchange and crisscross the valency. This represents how many of these ions, such that your charges cancel. 1 of Mg 2 plus and 2 of that N3 minus. And therefore overall, this is how many. So there's 1 Mg. There is 2 of that N3. So this gives you Mgn6 like this, so this must be Mgn6 like that. And that's the end of the 21 marks question. I think I'll leave it here for this first part of these topical questions on mole concepts, amount of substances for the AQA A Level 16 to 18 years old chemistry content. Thank you for watching. Don't forget to click the button on the bottom right to subscribe to my channel. Do follow me at ptet.chemistry, at ptet.chemistry on Facebook, Instagram, Twitter, and Telegram to get connected and to get in touch for personalized private tutoring if you need the help. And yeah, just get in touch and I'll be more than happy to take in you as a student. Thank you for watching again. I'll see you in the next tutorial video.